Welcome to Great Physics. In this video we'll be explaining the concept of packing fractions and a few other important details you may need to know. I remember when I was getting my head around this concept it could be hard to visualise things in 3D, so we wanted to give you a chance to see it for yourself using grapes and everyone's party favourite.
So, what is a packing fraction?
A packing fraction is the ratio of the total volumes of hard spheres to the volume of a given space, for example, tennis balls in a box.
And why do we even need to know about it?
Aside from it being in your exam?
Yeah.
A packing fraction gives rise to the macroscopic properties that help us understand why some materials have the characteristics they have, for example density.
So, where do we start?
There are a few terms you should know about before we get into it. A lattice. A lattice is an infinite set of identical points within a crystal. The points, in red, are lattice points. A basis, shown as stars. A basis is what's inside the unit cell. We'll get to unit cells in a second. A crystal. A crystal is a combination of a lattice and a basis.
Like salt.
Unit cell. Unit cell is the smallest repeat unit to make up a crystal. Lattice parameter. A lattice parameter refers to the dimension of a unit cell. Coordination number. Coordination number is the number of nearest neighbours by an atom or an ion. And a nearest neighbour is just simply the smallest distance between two atoms in a cell. In this course, we will only usually be talking about the first nearest neighbour, and especially in these circumstances. A lattice site. A lattice site is the number of full atoms inside the unit cell, not to be confused with lattice points.
At the heart of all physical concepts there lies an equation, so here is the one for APF. Na stands for the number of atoms in the unit cell, Va is the volume of one atom, and Vu is simply the volume of the unit cell. So now that's out the way, let the fun begin.
Important note, when referring to the volume of the atoms in a cell, we generally refer to the radius of the sphere as a function of the lattice parameter, A.
Now let's do what physicists do best. A grape is approximately equal to a hard sphere, which is approximately equal to an atom. But that's okay, we're physicists. This is acceptable. We will now go through the most simple case, which is a simple cubic lattice. If we take the front left vertex as our reference point and extend the lines, we can see that there are 6 nearest neighbours. Since seeing the lattice in 3D will make it easier to visualise, we will use our mighty grapes and cocktail sticks to do just that. Here is an awkward interval of somebody poorly assembling the lattice for you to enjoy.
That's me.
We can now see there are 8 lattice points for an SC. Now imagine our grapes, aka atoms, expanding into balloons.
It's magic!
The arrows on the balloon point towards the outline of where you can imagine a cube, which represents our unit cell as being. If we then take one of the atoms, aka the yellow balloon, in order to help us visualise what portion of one of these atoms is contributing to the unit cell, it is clear that it is 1/8. By using 4 SC unit cells, we can see why each atom is split into 8 parts. Essentially, each of them are being shared between 8 unit cells. We can now find the number of lattice sites. We know that each atom contributes 1/8 of its volume to the unit cell. We also know there are 8 lattice points. So by doing some simple maths, 1/8 times 8 clearly gives us 1, which is the number of lattice sites. This means that only one sphere can be packed into an SC unit cell. In order to find the APF, we will use the equation we saw earlier. To find the volume of the sphere, we need to know its radius. We can find this by taking a cross-section of the lattice. The radius is a lattice parameter A over 2. We find the APF to be 0.52. The next lattice structure is called a body-centered cubic. This is the same structure as a SC except with an extra lattice point in the center. Going through the same process as before, there are 8 nearest neighbours and 9 lattice points. For the number of lattice sites, it will be the same as an SC plus 1 due to the extra lattice point at the center. To find the APF, we must once again find the radius of each sphere inside the unit cell using our old trusted friend Pythagoras' theorem. First we find the diagonal across one face, x. Using this value we can find the diagonal across the centre of the lattice, y. By taking a cross-section of the diagonal, we see that y gives us 4 times the radius. We then go through the same process as before and find the APF to be 0.68. Our last structure is a face-centered cubic, which is the same as a SC except for 1 extra lattice point on each face. There are 12 lattice points in total. For the lattice sites, as before, there is 1 lattice site which comes from the SC part of this lattice. The 6 additional points on the faces are shared by 2 cells and therefore contribute 1/2 to the unit cell. So this gives 3 extra lattice sites. In total, for an FCC, we have 4 lattice sites. To find the radius of each of the spheres within the unit cell, we take a cross-section of one of the faces and find the diagonal x. This value is equal to 4 times the radius. To find the number of nearest neighbours, let's take the lattice point in red as a reference. The 4 points of the vertices of the same face, along with the 4 points on the faces of its unit cell, along with the 4 points on the faces of the neighbouring unit cell, contribute to the 12 nearest neighbours. We find the APF to be 0.74 using the same method as we have been using.
In summary, here is a table of all the important things to take away from this video, including a few examples.
If you're up for a challenge, try answering the following questions about a HCP lattice. To find the answers,
Google is your friend.
thank you for
watching.
Next time you're packing, remember your packing fractions.